Welcome to Waves, the MP4 PowerPoint video. Today's objectives: students will be able to explain the relationship among waves, energy, and matter, and describe the differences between transverse waves and compressional waves. What are waves? Waves are rhythmic disturbances that carry energy without moving matter. And we have two types of waves. One is the mechanical wave. It travels through a medium, while there's also an electromagnetic wave that does not require anything to travel. What carries a mechanical wave? What carries a mechanical wave is called the medium, the material which the wave travels through. Let's look at some examples. High frequency sounds that bats make, perhaps things in the ocean, or even a guitar string. Think about what those waves travel through. Once a guitar is plucked, where does that energy transfer out to? How does it go through? What does it go through? It goes through the air. And just like this frog in the pond, mechanical waves are produced when a source of energy, the frog, causes a medium to vibrate. The medium is the water. And mechanical waves, they don't move the medium. When a wave travels under a buoy, the buoy moves up and down, but the buoy does not travel with the wave. After the wave passes, the buoy and the water return to where they started. Two types of mechanical waves, one being a transverse wave. It means across. The particles of the medium move at right angles or up and down. An example of this would be water. If we were to diagram a transverse wave, you would notice that there's a crest, the highest point of the transverse wave, and there's also a trough, which is the lowest point of the transverse wave. The second type of mechanical wave is a longitudinal wave. It moves the medium parallel to the direction of the wave, back and forth, like a slinky if you think of it that way. An example of a mechanical wave that has this form is sound. Take a moment and contrast transverse and longitudinal waves. 1. Particles vibrate perpendicular to the energy source. 2. Particles vibrate parallel to the energy. Entirely new other type of wave is what's called an electromagnetic wave, and these waves don't need any kind of medium. They can go through space. These include microwaves, radio waves, infrared waves, X-rays, and gamma rays. But we need to take a look at it much more closely at the light waves that can travel through space, and we're talking about radiation. And it starts all the way over to the left, as you can see, is radio waves. Then you have microwaves, infrared. Then there's visible light, and then we have UV, which is ultraviolet. Then we have our X-rays, and then our gamma rays. If we look at our properties of waves, we can start with amplitude. The amplitude is the maximum distance that the particles of a medium will move away from their resting position. As you can see on the graphic, it's the highest part of the peak and the lowest part. Then we have our wavelength. Wavelength is the distance between two corresponding parts of the wave. So we actually take a look at peak to peak. We have a shorter wave, and we can compare that to a longer wave. Next we have speed. This is the rate the wave is traveling through the medium. If we put all these together, we get frequency, the number of complete waves that pass through a given point in a certain amount of time. This is measured in hertz. Okay, as we look at this beautiful picture of, I do believe this is Ontario, Canada, we're going to look at wave behavior: reflection, refraction, diffraction, and interference. What's great about these is you deal with these all the time. Number 1, reflection. When a wave hits a surface and bounces back. The law of reflection simply states this: the angle of incidence equals the angle of reflection. Very simply stated, the light that comes down and hits a surface is going to be reflected at the same angle as it was received. Now refraction. When a wave enters a new medium at an angle, one side changes speed before the other, and it causes it to bend. Waves move through different mediums at different speeds, which takes us to Sir Isaac Newton's famous prism experiment. The light is actually slowed down through the prism, and it actually breaks apart the different types of light. Red, orange, yellow, green, blue, indigo, and violet are separated because they're going at different speeds. Then we have diffraction. When waves bend and spread out around barriers or through openings, this is called diffraction. As you can see in the graphic, the waves are changing as they come across the barrier. Then we have interference. When two waves meet, there is an interaction. It can be constructive or destructive. My personal favorite example of this is the old terrestrial radios. If you get too close to a different station, what happens? It interferes. It'll actually start bleeding into another station. And finally, we have resonance, an increase in the amplitude of a vibration when the external disturbance matches the object's natural frequency. My favorite example of this is if you have two identical cars with the identical engines that are vibrating at the same frequency and they completely line up, you can have amplification, and it'll actually start rocking the car back and forth because you have what's called resonance. So this is the end of today's waves lesson. I hope you learned a lot, and we'll see you next time.